video, I'm going to introduce vectors and specifically two-dimensional vectors. So a vector is a directed line segment. So at heart, it's a geometric object. And that's something that we often forget as we move along. We're going to talk about a lot of coordinate systems and changing between coordinate systems. But at its very heart, a vector, we need to remember, is simply a directed line segment. It's a geometric object that doesn't really need a coordinate system. So it has direction and it has length, which represents a magnitude. In other words, this vector right here might be a 50 Newton vector, meaning it's a 50 Newton force, which is about 10 pounds, directed in this direction, whereas this might be another 50 Newton force directed in this direction. And we know that if this is a 10 meter per second velocity and you're standing here as opposed to, say, here, that's different from a third person standing here. Okay, so you're approaching this person, moving away from this person, and you're really doing nothing compared to this person, right? So 10 meters per second is the magnitude, but the direction is very important when we're dealing with vectors. So specifically in this video, we're going to address two-dimensional vectors, and in a later video, we'll advance to three-dimensional vectors. So we're talking about vectors as opposed to scalar, which is only a magnitude. So like in the last example, I pointed out that 10 meters per second, this was the magnitude, and if we had no vector to refer to, then that would be a scalar. So there are lots of quantities in physics and other branches of science which are vector quantities, and they have magnitude and direction. Now, generally what you're going to see is a vector is written in bold print or with an arrow above it, above the letter, to indicate that it's a vector. And I'm probably going to be pretty sloppy in this video, and I apologize in advance. But some examples of vectors would be 60 miles per hour, which is just a magnitude. That's a scalar because there's no direction implied. So 60 miles per hour east, however, is a vector. Okay, because it has a direction. 60 miles per hour south is a different vector, different direction. So it has the same magnitude, but different direction, making it a different vector altogether. All right, so what are vectors and not vectors then? As some examples, okay, force is a vector, like your weight is the gravitational force of the Earth pulling on you, and it pulls toward the center of the Earth, so it has a direction, and as opposed to mass, which has no direction. Velocity has direction, speed does not. Acceleration has direction, and I didn't pick not a vector or a counterpart for it because we could take the magnitude if we wanted to call it that. Length is not a vector, but displacement is. So for example, let's say you're going from A to B, or at least we have a distance between A and B. So this is a length. All right. Now, if we add an arrowhead to it, that becomes a displacement. All right. So this displacement is distinct from this displacement, and this is merely a length, the distance between two objects without respect to direction. So when we designate direction, we're talking about 0 degrees starting at what we normally would call the x-axis, but I don't want to call it the x-axis because I want to concentrate on its polar coordinate aspects. So this is a polar coordinate system. So here is, we draw a ray and we call it 0 degrees. And then we rotate our vector with the starting end at the origin, moving around counterclockwise for positive angles and clockwise for negative angles starting from 0. So for example, I can rotate 23 degrees. I can rotate it more than 23 degrees, and I can keep rotating it clockwise, and I can rotate it without end. I can rotate it as far as I want. So those are all positive angles. All right, so let me get rid of those. Okay, and so these are negative angles. Okay, so this might be negative 40 degrees. All right, and you can rotate in a negative direction all you want, as much as you want, to infinity. All right, and then you go out a certain distance from the origin. That's the magnitude, the length of the ray. All right, now angles are used to denote the direction of vectors, so we have to really kind of talk about angles, and there are two types of angles that we need to figure out before we go too much further, and there are standard angles. Those start on the positive x-axis and they rotate counterclockwise for positive and clockwise for negative, all the way from negative infinity to positive infinity. So what that means is I can have a positive angle, such as this one, and wherever I stop rotating, that's my vector. Okay, so I go out r, maybe I should pick a different color, go out length r from the origin, and that's my angle. Okay, so I can go all the way to positive infinity. So in other words, it's really all real numbers. So standard angles take on, or the same as the real number set. All right, and if I want to go in the other direction, let's get rid of the red line for now. Okay, in fact, let's get rid of this. But if I want to go in the other direction, that's a negative angle. Okay, so let's go this way. There's my vector. There's r. There's my theta. Okay, and that would be a negative. And I can keep going round and round and round until my hand gets tired and go all the way to negative infinity in the other direction. Okay, so those are standard angles. Okay, so I can have a standard angle of 15,000 degrees. I can have a standard angle of negative 27.8 degrees, and so on and so on. Okay, so there can be any real number from negative infinity to positive infinity. Type of angle, or reference angles. All right, now reference angles only go from 0 to 90, and they describe the terminal position of the vector in a certain quadrant. So for example, and this is probably best taught by example, okay? So let's take, for example, I'm going to draw in 4 30-degree reference angles. Okay, so degrees, degrees, degrees. So I'm measuring the angle from the closest x-axis to the vector. Okay, so I'm going to call these my vectors. Okay, and let's get back to your business here. Okay, and so I've described direction in the 4 quadrants that describe the Cartesian grid using 4 30-degree reference angles. Okay, so in the first quadrant, 30 degrees is 30 degrees. This is the standard angle. Okay, in the second quadrant, let me choose a color, different color. Okay, so this is 150 degrees. So that's the standard angle for a 30-degree reference angle in the second quadrant. So remember, the quadrants are quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Okay, moving along. Okay, let's go to, okay, so this would be 210 degrees. I did 180 plus 30, and 210 degree standard angle corresponds to a 30-degree reference angle in the third quadrant. And in the fourth quadrant, if I continue this process, and I'm going to get rid of some of these lines to get rid of the clutter. Okay, and if I continue around, this standard angle would be 330 degrees, and all I did was 360 minus 30 to get the standard angle. So this standard angle corresponds to a 30-degree reference angle in the fourth quadrant. So notice that there were 4 distinct standard angles for one 30-degree reference angle, at least between 0 and 360. Okay, and the reason I'm pointing all of this out is because when we get to going back and forth between magnitude and direction and components of a vector, this function right here is going to return only reference angles, and we have to be very careful in using it. It's not very difficult, but you just have to pay attention to the plus minus sign. All right, so let's try that again. 40, 40, 40. So let's do the standard angle in green. Okay, so the standard angle here is going to be 40. In the second quadrant, this is going to be 140. This one's going to be 220. And this one's going to be 320. So here's your standard angle. Here's your standard angle. There's the standard angle. And hopefully I can get this one in. There's your standard angle. All right. So a lot of times, many books, textbooks, you're going to see a vector expressed in terms of the Cartesian coordinate system, okay, where we consider the tail of the vector to coincide with the origin and the endpoint to coincide with some ordered pair. All right. So here's your ordered pair. Okay, there's the origin, there's the directed line segment, the arrowhead on the end. Okay, and with this ordered pair, you can correlate that to a radius or a length of the vector and an angle theta. All right, and that's what we're going to do now. So basically what this amounts to is a conversion, set of conversion equations between polar coordinates and Cartesian coordinates. All right, so x equal arc cosine theta gives you the adjacent side of the right triangle, the segment along the x-axis, okay, and this is the y coordinate, okay. So if we were plotting the ordered pair, we'd go out x units and up y units and plot our ordered pair right there. That gives us a right triangle whose hypotenuse is r. So basic trig gives us these conversions. And then this is really just the Pythagorean theorem. Okay, it's where the hypotenuse is the square root of the sum of the square of the legs. This function right here, inverse tan, is the one I was warning you about and we have to be careful about. And it's best to show you what I'm talking about by example. But I will say this, that the only thing that this function is going to return to you are reference angles. Okay, so you must be wary of what you're completing an assignment. Okay, so what we're going to do is let's break this vector into component vectors first before we go hog wild with inverse tan. All right, so let me get my notes. Okay, I'm going to call this vector v because it looks like a velocity vector. I'll try to use my notation like I'm supposed to. All right, so Vx is going to be 45. We'll leave off the units. Cosine 23. Make sure you're in degree mode. Okay, and Vy is 45 sine 23. And again, a reminder, pause the video if you need to. Okay, and I'm just going to pretend that that you have and that you come back, okay? All right, so okay. So 45 cosine 23 degrees gives us 41.4. This gives us 17.6, and the units which I left off are miles per hour. So the units for the components are the same unit as the magnitude of the original vector. Okay, so those are the components. Let's see. So if we call this one green, that's this one right there, and it is a vector in its own right, I might add. Okay, and then this one right here is right here, which is also a vector in its own right. Okay, because we'll talk about unit vectors or basis vectors in a later video. All right. So those are vectors in their own right, and they could form, if you want to think about it, they could form what we call a basis. So how about if we start with the components? So we have the Cartesian components. Okay, so this is like the x component, this is the y component of a velocity vector. Calculate the magnitude and direction of the vector. Okay, so if we're calling it a velocity, we denote magnitude by absolute value. Okay, so the magnitude of the velocity vector is 6 squared plus 8 squared, which is the square root of 100, which is 10. And it's going to have the same units as its components. Okay, that would, I think, stand to make sense. Okay, so this is 10 meters per second right here. Okay, and this is the first quadrant vector because both the magnitude and direction are positive, just like any ordered pair where you have plus plus. Okay, then that denotes first quadrant, and that's sort of the thing I was talking about earlier with with this function right here. So inverse tan, I'm not thinking. Okay, so inverse tan is the y component over the x component, and that's going to give you, get my notes, that's going to give you 53.1 degrees. And you can provide north of east if you want. If you don't, it's normally understood because we are in the northeast quadrant where this is north and this is east. And we rotated the vector, if we start here, we rotated it in a northerly direction of the east beginning direction. That's why it's called north of east. All right. So back to this function right here, you have to be aware that the only thing this thing is ever going to return to you is an angle between 0 and pi over 2 or 0 and 90 degrees, depending on whether you're working in degrees or radians. So in the first quadrant, adjacent and opposite sides plus plus, or x and y components if you want, okay? And so in the second quadrant, x component is negative in the second and the third quadrant, okay? Y component's positive, y component's negative. So it's negative, 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 positive. Let me, hold on, I realize you're not seeing that. Okay, so let's start over. Okay, so plus, plus. All right, negative, positive, negative, negative, positive, negative. So you start at the origin, you want to go end up at the end point back here at the end point of your vector, and you trace along the legs of the right triangle. and you're either going in plus or minus direction for x, plus or minus direction for y. And that's important to keep track of, because the thing that you find out, let me erase all this, so I'm going to start afresh. Okay, so the thing that you find out is, for example, and you can do this with the calculator along with me if you want, but if you take the inverse tan of, let me pick one, let's just do -1 over -3, which puts us over here in the third quadrant. Okay? What you're going to get is you're going to get 18.4 degrees. Okay? So if you take the inverse, and I meant to put inverse tan, if you take the inverse tan of 1 over 3, you're going to get 18.4 degrees again. Okay? So the reason for that is because these negative signs right here, they cancel out. So by the time your calculator takes the inverse tan of this ratio right here, it doesn't know that you divided one negative number by another negative number. Okay? So it can't tell. You can, however. So you have to keep track of the signs of the units. The same sort of issue happens in this quadrant and in this quadrant, because these are both negative quadrants for tangent, and inverse tan operates the same way. It's going to return a negative angle, but it doesn't know whether you're in the fourth quadrant or the second quadrant, because it doesn't know which was negative and which was positive, the numerator and denominator. Okay? All right, so let's okay, so I'll just do what I was going to do here. Okay, and so when we're talking about that bow tie type figure that I just showed you, you have north, west, east, south, and I hope our map skills are up to speed, because I noticed that some kids don't know north, east, west, and south, but I'm hoping that you do. All right, so in the second quadrant, if you use reference angles, we denote that we're in the second quadrant with north of west. We can use north of east, although it's kind of understood if you leave it off, south of east, and south of west when dealing with reference angles. Okay, if you're dealing with standard angles, you don't need these. You don't need these designations right here with standard angles. You need these with reference angles, the ones that go between 0 and 90. Okay? All right, so we're going to take a vector with a magnitude of 14.5, and I'm not going to worry about the units, okay, because we're not really doing any specific physics right now. Okay, but what I want to do, and again, pause the video if you want to do it before I do it. I'm taking time to erase all this. Okay, there we go. All right, so what we're going to do is break this into x and y components, and we're in the northwest quadrant. So x is negative, and the y component is positive in the second quadrant, just like an ordered pair. If you were plotting an xy ordered pair right here at this position in space, its x would be negative and the y component would be positive. Okay, so there's a direct correspondence between those two concepts. All right, I'm going to call this vector r, so it can call this rx. Rx is 14.5 cosine 42. Ry is 14.5 sine 42. Now, since 42 is the first quadrant angle, and I know the x component is going to be negative, I have to supply it, meaning I have to write it down. Okay, so that's important. Okay, so this is going to be negative. Let me catch up with you. All right, so this would be negative 10.8, okay, because I used a reference angle. And this is going to be 9.7. Now, let's pretend we'd done this calculation all over again. If you wanted to do x equal 14.5 and you didn't want to worry about signs, you could do 14.5 cosine 138. So 138 is the standard angle for this 42-degree reference angle. Reference angle, standard angle. Now the calculator, when you use 138, the calculator knows you're in the second quadrant and gives you negative 10.8. So we end up in the same place using two different types of angles. That's essentially what I'm getting at here. All right, let's try another. So pause the video if necessary, okay? All right, so Rx will be, and by the way, this is going to be negative, negative. So negative Rx, negative Ry, okay? So it's going to be negative 4.5 cosine 32 Ry be negative 4.5 sine 32, and I'm going to get negative let's see, actually didn't do those, 3.82, and here I'm going to get negative 2.38. All right, those are the components of this vector. So magnitude, direction, xy component, Cartesian coordinates, or Cartesian components. Okay, so what other way could I have accomplished this one? Okay, well, this one for that matter, I could have done the same one. I could have done both of them the same way. I could have done disregard the sign, don't worry about supplying it, like writing it in, and do cosine. I believe that's 212. Yeah. So 212, 4.5, sine 212, and your signs come out automatically because the calculator knows what quadrant you're in. It can't know. It assumes if it sees 32, it assumes first quadrant. And in the first quadrant, cosine and sine and tangent, everybody's positive in the first quadrant. All right, let's try another one. So now we're in the fourth quadrant. So in the fourth quadrant, the x component is positive, the y component is negative. So if I'm going to use my reference angle, I'm going to do 75 cosine 58 positive, Ry could be negative 75 sine 58. And I'm going to get, for this one, $39.7. And here I'm going to get a negative 63.6. Whether you write it in right here or not is unimportant. What is important is that you recognize it's negative at the end before you shut things down. Okay? So what's the standard angle for 58 degrees in the fourth quadrant? Well, I would do 360 minus 58, and I get 302. So if I had done 302 degrees here and here, the calculator would give me the negative sign. I wouldn't have to worry about it. Okay? All right. Okay, so given components -3 and -7, let's go the other way with our conversion between Cartesian and polar coordinates. Okay, so -3, 7 is over here in the second quadrant. Okay, that means I go out -3, just like any ordered pair, and up 7. Okay, and there's my vector. Okay, in fact, let me change that color there. So there's my vector right there, okay, in green. Let's call it vector R. Okay, so R is equal to the square root of 3 squared plus 7 squared. Notice I ignore the negative sign with the 3 right here because it's going to turn out positive anyway. And if you key this in incorrectly in your calculator, you're going to end up out in space and get something like a -9. So just ignore the sign, take my advice, and just ignore it. Okay, when doing this, I'm not saying to ignore it from here on out. So the magnitude is approximately 7.62, and that should be a 2. Okay, the angle, here's where this thing comes in. Okay, so the angle is inverse tan of 7/3. Notice I ignored the sign in here. Okay, I'm not worried about it because the only thing it's going to give me is a negative reference angle, and that doesn't help me. It could be either in the fourth quadrant, it could be in the fourth quadrant, or it could be in the second quadrant where we already have it drawn, and the calculator will not tell me beyond that. All right. So this is 66.8 degrees, and since it's in the second quadrant, I have to denote that by saying north of west, or if I want the standard angle, I'll do 180 minus 66.8. And the standard angle is 113.2, and I don't need this. Okay, so it's either this or this for the direction, and here's your magnitude. All right, let's try another one. Pause the video. Okay, so we're at -5, -7. Okay, so -5, -7, -5. Okay, here's my vector. It looks like Christmas. Okay, so this is vector R. Okay, it has a direction and a magnitude. All right, so R is equal to the square root of 5 squared plus 7 squared. And I get 8.6 for my magnitude. Theta is inverse tan of 7/5. It's always the y component over the x component for inverse tan. And that's going to give me a reference angle of 54.5 degrees south of west. Okay, or if I choose, I'm going to do 180 plus 54.5, which gives me a standard angle of 234.5. So this, let's try a different color. Okay, so, all right, so this for your direction, either or, and here's your magnitude and direction. All right. Check your understanding. Find the x and y components of the vector. Here I would expect you to, if you haven't done any yet, please pause the video and do this on your own. So we're talking about a force vector. All right. So f of x is -52 cosine 82. So we're north of west. I kind of skipped a step there. So we're in the northwest quadrant. Here's north, here's west, here's our vector. Well, and the associated triangle with it, okay? And so I know that the x component is negative, the y component is positive. if I'm using a reference angle, I have to supply those signs, plus and minus signs. So negative 7.24 newtons, same unit as the original vector. Okay, and then Fy should be 52 sine 82, and you get 51.5 newtons. And those are your components, the x and y components of that force vector. Let's try. Okay, so here we're given x and y components of a force vector, and we're asked to find the magnitude and direction of the vector. All right, so proceeding then, the magnitude of this vector. So I'm being very persnickety with my notation here, very careful. So it's going to be 2.53 squared plus 1.67 squared equals, so you square each one, add them, and then take the square root. So you may need to brush up on your order of operations. In doing these videos, I have to assume a certain skill level in order to not reinvent the wheel each and every time. Okay, so 3.03 newtons is your magnitude, and theta is, and by the way, again, I kind of jumped the gun there. All right, so what quadrant is this vector in? The vector is in the fourth quadrant because it's plus x minus y, and your vector is right here. Okay, so that's your force vector. So this thing right here is 3.03 newtons long. All right, so this is going to be inverse tan of 1.67 over 2.53, and I get a reference angle of 33.4 degrees, which is the only thing this will ever give you back is a reference angle. It's never going to give you something like 234 degrees. South of east, and the reason I know this is because I'm looking at the plus and minus signs of my coordinates. Okay, so here's south, here's east. I'm south of east, and if I want to, I can say 360. If I prefer a standard angle, I can do that. I'm going to get 326.6. Okay, final color to wrap things up. I don't want it to look too much like Christmas. Okay, so we just got finished with Christmas. So there's your standard angle. So both of these suffice as the direction, either one or the other. You wouldn't do both. Okay, and then there's the magnitude of your vector, magnitude and direction, which is what we were asked to find. All right. So just to recap, you have basically what we're doing is converting between polar and Cartesian coordinates. And we have to be aware of the difference between reference angles and standard angles when we're doing that. All right, so I'm hoping that you find these videos instructive.